Okay, so for problem number 8, I have chosen to skip number 6 and 7. You guys can do that on your own. Number 8 is actually problem number 7 if you consider just these regions. And there's a typo in here. That should be A is less than R, which is less than B. So if you can do A1 and 2, then you can also do number 7. Okay, the first thing is we've got this unique type of conductive wire, and there is a wire in the center that has a current going to one direction, and then there's a conducting tube that has a current going in the opposite direction. And the cross-sectional image of that is right here. And it tells us that the current is evenly distributed over the cross-sectional area of each conductor. So both the tube and the inner wire. So first thing we're going to do is find R less than A. So this is my Ampere's loop. And this is my radius R. And because it is a loop that is within the wire, we need to figure out what I enclosed is. So the fact that the current is evenly distributed means that I enclosed over the cross-sectional area, which is pi r squared, is equal to the full current over the entire area, which is I big R squared. Now, I simplify this and get I enclosed is equal to I little r squared over big R squared. And then we plug that into our Ampere's law, which is the enclosed integral of B ds is equal to mu naught I enclosed, which we have established as I little r squared over big R squared. ds is the Gaussian loop, and every small section of that Gaussian loop is ds. So as we go through the entire loop, we're going from 0 to 2 pi r. So this is b times 2 pi r is equal to mu naught I r squared over big R squared. This little r reduces that r, and we get b is equal to mu naught I r over 2 pi big R squared. So here we've got our expression for A, and I'm going to go straight to the graph. I can see that B is proportional to R, everything else is a constant, so I'm going to show a linear function for R less than A. The next one we're going to do between A and B. So that's going to be this Gaussian circle right here. And this one is easy because we've got the, we have the Gaussian equation, and I'm just going to go ahead and plug in that 2 pi r is equal to mu naught I enclosed, and I enclosed is just the inner current of that inner wire, which is just I. So I get mu naught I over 2 pi r. That gives us an inverse function. That means B is inversely proportional to R. So in that section, we're going to decrease exponentially. Okay, so for part 3, we're going to have a Gaussian surface all the way out here. And we want to look at our I enclosed. So I'm going to do this work in red. Our I enclosed is the total current inside our Amperian loop. I have a current going into the board for the inside wire. I have a current going out of the board for this outside wire right here. And that means that since they're going in opposite directions, the currents are going to cancel out. So I have a current of I going in minus a current of I coming out, which means that the total enclosed current is 0, which means that the magnetic field outside of the apparatus, this entire conductor is 0. So let me draw that in right here. Okay, so what happens in between B and C? Now that's a really tricky question, and what we want to think about is the fact that because the charge is uniformly distributed, we have to figure out I enclosed. So if I were to take my Gaussian sphere somewhere here in the center, and that's going to have a radius of r, I need to figure out my I enclosed. So I'm going to do when r is greater than b but less than c. You don't have to go through this entire process, but I just wanted to show you kind of why it looks the way it does. It's the fact that our I enclosed is kind of this inner part of the sphere, not the full, or the inner part of the tube, not the full tube. And so I need to take the I enclosed over just that tiny sliver of the tube. That would be pi little r squared minus pi b squared, because that's the full inner sphere. That's equal to the full I of that tube, which is pi c squared minus pi b squared. And then from there, I get I, and let me pull out the pi. Oh, actually the pi's end up canceling out. That makes things easy. Times r squared minus b squared all over c squared minus b squared. And then what we also have to do is include the fact that there's also this inner current right here, and that inner current is going in the opposite direction. So the way I did it here is the current going in is positive, the current coming out of the board is negative, and when I simplify this, I get I r squared minus I b squared. And then I'm going to multiply the denominator to this I over here. Oh, and also I have to distribute, so this becomes a positive. And then I get plus IC squared minus IB squared. So that gives you a common denominator. And then you'll notice that we've got some of these values canceling out. And we end up with, I'm just going to pull out the I. C squared minus R squared all over C squared minus B squared. This whole thing is equal to B times 2 pi R. So I'm going to set B is equal to 2 pi R in the denominator. Okay. So what we have here is we've got an R squared and we've got an R. Those will end up reducing. But what we also have is the fact that this R squared is negative. So if you made up some values for C squared and B squared, you would be able to pull out some number of values, and in essence, if we just simplify everything down, we would get a bunch of constants out here, and then essentially some number, let's just make it easy, 1 minus R squared all over r. And when you graph this function, you can go ahead and just plug it into your calculator. You end up with a function that looks like this. So it does take on a very similar shape as this exponentially decreasing function. It's a little bit sharper and it goes through the origin, which our r1 over r wouldn't do. But we do know that we end up at 0 at c. So I'm just going to create that shape, but then stop it at c. This should be kind of more curved. And then go straight through 0 at c. So again, this work is unnecessary. I just wanted to show you kind of the general equation of what happens when you have a kind of enclosed current in a tube. But it's just good to note that they all kind of decrease in that upward facing concave up curve when it is going further and further away from the center. And then the only linear is when it's 0 and when it is within the inner conductor. So last is if the current in the tube is reversed to opposite, how would it change your answers to A, 1, 2, and 3? Well, if they were going in the same direction, so let's say, what is it? Current in the tube is reversed. So that means that the tube is going to be also going out of the board, or sorry, into the board. Then what we would have is, first of all, our internal B stays the same. Our enclosed charge is going to be the same whether the outside has switched or not. The external currents don't really affect anything. Same thing with 2. The fact that the outside current is switching doesn't change the magnetic field when it's within that tube. So that's also going to stay the same. So let's write this down. For 1, it'll be same for 1 and 2, but if you want to write it down, it'll be mu naught I r over 2 pi r squared, big R squared, and then this one would be mu naught I over 2 pi r. And then for the third one, you now do have to take into consideration the direction of your current. They're both going in the same direction, so I same direction, and so the sum of your i's, or the I enclosed, is equal to 2i, and then you just plug that into your b2 pi r is equal to mu naught I enclosed, which is 2i, and then you can reduce things and you get b is equal to mu naught I over pi r. And that would conclude problem number 8.